Yeah, should I start? If you want. Okay. Okay. Thanks for the invitation, and I would like to thank the organizers for hard work in putting uh, this workshop together. Um, I, I want to talk on abelianization of Skein modules, and since probably not everyone is familiar with what Skein modules are, let me start by defining what it is. Okay, so in general, a Skein module depends on a choice of a ribbon category, but we, which in this talk we'll basically take um, as a category of representations of quantum group UQSL2. Um, so given such a choice, a Skein module assigns a vector space so to each 3 manifold. So for each 3 manifold Y, we got a vector space called the Skein module that depends on the choice of a ribbon category. Um, so in this particular choice, when this ribbon category is just the representation category of quantum SL2, sorry. The Skein module has a particularly simple description. So in this case, I'm going to denote it by SK for Skein and SL2 just a shorthand for this ribbon category. The Skein module of Y is defined to be the formal k-linear combinations where k is the choice of a base field. Of framed unoriented links and Y. So this itself will be a huge vector space. But modulo, we consider it modulo the so-called Skein relations. And the Skein relations in this SL2 case are given as follows. So you're probably familiar with this if you're familiar with Jones polynomials. So if you have a framed unoriented link in Y that looks locally like this picture near a small ball, then that we impose a relation that's equal to the following linear combination, where this picture denotes the length that looks exactly the same as this one outside of the ball, but slightly modified inside this ball by resolving a crossing, plus a inverse of a length that's resolved in the other direction, where A is just some element in our base field. We also have another relation that allows us to remove any unknot component by a factor of minus a squared minus a to the minus 2. So we just get rid of this unknot factor and then we multiply everything by this factor. Yeah, so it's some vector space formally defined in this way. Yeah, so if you haven't thought about Skein modules before, you might be wondering why one should care about Skein modules at all. There are many reasons. In particular, for instance, it's Skein modules is our natural place to count open topological strings. Skein modules for three manifolds, they're supposed to be the Hilbert space associated to three manifolds in Kapustin-Witten theory, etc. But for our purposes, probably the most important feature of Skein modules is the fact that the Skein module quantizes the character variety. The SL2 character variety, that is the moduli space of flat connections on Y with SL2C gauge group. So a couple of weeks ago during the training week, if you were here, we saw in Lotte Holland's talk that using spectral networks, we get a stratified abelianization of an SL2C flat connection. And well, that was for the case of surfaces, but in fact, there is an analog for the case of three manifolds. Indeed, in a recent work of Dan Fried and Andy Knightsky, they basically tells us what are the natural three-dimensional analogs of spectral networks are. And using that, they gave a procedure of abelianizing SL2C flat connection in an ideally triangulated three-manifold. And given the fact that Skein modules quantize character variety, a natural question is whether there's a story, whether there's a quantum version of abelianization. Since I believe most people in the audience are physicists, here is the relevant physical setup. So we're going to consider the fibrane theory of type gel N on a three-manifold Y, say times a complex plane, times R. And we're also putting an omega background in C. Let me denote it by this U1 rotation symmetry by U1Q. And we're also going to put a surface defect that's sitting on some link L in Y times the origin times R that is colored by some representation of gel N. So if you view this, if you compactify on Y, these surface defects would correspond to some line defects in 3D n equals 2 theory, T of Y, gel N on C times R, and a line defect along the origin of C times R that is labeled by a choice of a link and a representation of GLN. Um, just like in case of 4D equals 2 theories of class S, where as you go to Coulomb branch, we get a spectral curve, which is a branched cover of our UV curve. As you go to IR, we're going to get some branched cover of Y that is an n-to-1 cover. And this theory we had in the UV, the T of Y of GLN, basically becomes the theory based on this branched cover with GL1. Um, oh, it is known, or at least conjectured, that these surface defects actually only depend on a choice of an element of a Skein module rather than actual choice of a link. Meaning, so we're considering some vector space of line defects labeled by elements of the Skein module. So as we flow from UV to IR, there should be a corresponding map of line defects. That is, we start in the UV, we start from the Skein module of Y based on a quantum group of GLN, and there should be a homomorphism or a linear map from this Skein module to line defects in this IR theory, which would be the GL1 Skein module of this n-fold branch cover. Yeah, it's an embedding. It would be some graph of a harmonic one form. In fact, so this problem of finding this homomorphism can be solved explicitly in case of surfaces and branch double covers. That's the work of Andy Knightsky and Fei Yan, I think from 2020, where they constructed they constructed a map from Skein GL2 Skein module of a Riemann surface times R to GL1 Skein module of a branch double cover times R using using spectral networks. And basically their construction is by counting certain flow lines given by the WKB foliation on the Riemann surface. So this Abelianization story, in case of surfaces at least, it turns out that this map they constructed has already appeared in math literature in a slightly different form. So this is an older work of Bonahan and Wong, I think from 2010, where they constructed a homomorphism from this SL2 Skein algebra of a surface. Let me denote SK-alg for Skein algebra. Okay, sorry, I forgot to say that even though it's a priori just a vector space, when the three manifold is a surface times interval, then because we can, if we have a surface times interval, we can stack one surface times interval on top of another. This stacking gives algebra structure, so that's why we often denote it by Skein algebra rather than Skein module. Anyway, so Bono and Wong constructed a homomorphism from Skein algebra surface to what's often called the quantum Teichmüller space, which is another quantization of the character variety of surfaces, where each coordinate chart in this quantum Teichmüller space is a quantum torus, meaning it's described in terms of Laurent polynomials and Q commuting variables. And in fact, one can show that, or okay, at least what Andy and Fei paper, they conjectured that this map is basically equivalent to this map they constructed using spectral network. I should emphasize that this map of Bono and Wong is purely topological or combinatorial and does not use a spectral network. Anyway, yeah, so there seems to be at least two different approaches to abelianization of Skein modules. So there is a story of abelianization of Skein modules using three-dimensional spectral networks and counting holomorphic curves, etc. But that's not going to be the topic of this talk. I'm going to focus on generalization of this Wong to three manifolds in this talk. For three manifolds, there is a natural analog of quantum Teichmüller space, which is a quantization of another quantization of character variety of three manifolds. That is sometimes called the quantum gluing module. I think the earliest form of quantum gluing module, even though it's not stated, I don't think this term is used. I think the earliest form appeared in this paper by Tudor Mofte, in his paper on quantum Riemann surfaces and Chern-Simons theory. So what it is when the three manifold is ideally triangulated, it has local coordinates given by the so-called shape parameters. And those coordinates or those coordinate functions gets quantized to Q commuting variables. And then there are relations that we need to mod out. So for the interest of time, let me just say that quantum gluing module is some quantum torus which gets, and we take a left and right quotient by imposing certain relations on the left and on the right. So the goal is to construct this map, which will be a three-dimensional analog of Bono and Wang's map, sometimes called a quantum trace map. And as a result, we would be relating two different well-known quantizations of character variety. Uh, oh, well, the way the right-hand side is defined is, so this thing, let me denote it by QGM. This thing depends on a choice of ideal triangulation of Y. And in classical hyperbolic, three-dimensional hyperbolic geometry, there are these shape parameters that kind of that tells us what shape the ideal, what they look like, and those coordinate functions gets quantized in the quantum gluing module. So it does not use Hegert splitting, and I don't know how to relate this with that approach. Yeah. Okay. Yeah. Maybe we should talk after. Yeah. I didn't fully understand yeah, what you're proposing. So, okay. Mm. Okay, maybe let me just also make a remark that I mentioned that there are these two different approaches to abelianization. One was to use spectral network, and the other one is this combinatorial version. There's definitely benefit in pursuing these different directions. It's because in this combinatorial version of so this construction and the construction that I'm about to give, basically this is a joint work with Sam Panich. For these approaches, it's kind of clear what we should do to generalize it to higher rank for SLN. Whereas when it comes to spectral networks, counting flow graphs becomes increasingly complicated for higher rank. So this approach seems to be much more practical when it comes to actual computation. Okay, so yeah, there are two main ideas. The first main idea is to use locality of Skein modules. What do I mean by this is that instead of just studying the Skein module of a whole three manifold, we can cut a three manifold into elementary pieces, such as ideal tetrahedron, and then construct this map for these individual pieces. But for that, we need to extend the notion of Skein modules, because if there is some link in a three manifold and we chop the three manifold up, then the link will no longer remain as links. There are going to be some tangles ending on endpoints of the boundary. So to that end, let me define the following notion. A boundary marked three manifold is a pair Y and gamma, where Y is a three manifold gamma is an oriented graph embedded in the boundary of Y, yeah, such that each vertex is either a sink, meaning all the edges adjacent to that vertex is oriented toward the vertex, or a source, which is the other direction. So just as an example, a tetrahedron, let's take Y to be a solid tetrahedron. Then we can take this graph, for instance, to be the following graph on the boundary. So on each face, we're going to draw a Y-shaped graph. And we put orientation in such a way that they're all oriented toward the center of each face. Then, yeah, this is a graph whose vertices would be like one on each edge, one on each face, etc. And the vertices on the edges are the sources. The vertices at the center faces are the sinks. So given a boundary marked three manifold, a stated tangle in a boundary marked three manifold is a tangle inside Y, which end on whose boundary points must lie inside this graph gamma. Yeah. 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 So there are vertices at the center of each. Yeah. These are vertices as well. Yeah. Yeah. Exactly. Yeah. Thanks for the question. Yeah, a stated tangle is a tangle. Is a tangle in this pair where the endpoints end on the mark. So yeah, something like this. Oh, sorry. Okay, so this is a tangle inside this pair. I didn't explain what stated means. So a stated tangle is such a tangle with with an assignment of a state, which is just a sign, either plus or minus, at each endpoint. So in this picture, well, this simple tangle has two endpoints. Let's say it's plus minus. So this would be an example of a stated tangle. Which local system are you talking about? Yeah. Maybe let me just say that okay, I don't know if this will be an answer to your question, but so basically this boundary markings, they're encoding or modeling some information from three-dimensional spectral network. So if okay, in a 3D spectral network, we have our three manifold has a one-dimensional foliation, which is analogous to the WKB foliation for surfaces, and the space of leaves, or the leaf space, would be some sort of foam, and these boundary markings are the boundaries of the foam. That's what. Yeah, Okay. Um, in terms of character variety, right. So ordinarily, an element of a Skein module, yeah, in the classical limit, yeah, that by taking the trace of holonomy, that would give us a function on the character variety. But now we're talking about free manifolds with boundaries, so have to specify some data. Okay, so yeah, I think this would be the, so in the setup of 3D spectral network, basically what you do is uh, at each puncture or at each cusp point, we need to specify a flag or um, let's say, okay, so what? Yeah, what? Like, I mean, one can ask an analogous question in 2D, right? And in 2D, what you do is have a spectral network, take a dual triangulation of a Riemann surface. Let me draw a spectral network in green. Um, so around each puncture, so we take a line, um, we take an eigenline, meaning we're fixing a Borel um, at each uh, at each puncture. Um, and parallel transports from these punctures to to the part of to the top dimensional stratification of this spectral network gives us the stratified abelianization in that story. Yeah, so the boundary marking is kind of a is the space of leaves. So in this case, that would look something like this with red lines. Yeah, I mean, either way, this yeah, it becomes clearer if we pass to abelianization. Then this such a tangle would really represent, so these states that we assign either plus or minus, that would correspond to a choice of lift to either sheet number 1 or sheet number 2. And then this would really, the corresponding function would really be the holonomy in um, in GL1 stratified abelianization. Yeah. Uh-huh. Yeah. Oh yeah, yeah, yeah. Sorry, so yeah, yeah, maybe that's the best better answer. Yeah, so yeah, yeah, I should have said that there's a classical version of the trace map, which would really be just computing this, yeah, matrix element, where yeah, plus and minus are the really just the two basis vectors in the fundamental representation of SL2. So yeah, it's really the matrix coefficient of the parallel yeah, of the holonomy or parallel transport. Yeah. Yes. Thanks for the questions. Okay. Okay, we have state tangles. Then, okay, I said we need to extend the notion of Skein modules to be able to study Skein modules locally. That's this notion often called stated Skein module. Yeah, maybe more after that. Yeah. So a stated Skein module, probably better called a relative Skein module since it's relative to the boundary, is basically defined in the same way as the usual Skein module. It's the it's a span of all the isotopy classes of stated tangles. Okay. In the boundary mark 3 manifold modulo stated Skein relations, where the stated Skein relations include the usual Skein relations that I wrote earlier, plus 2 extra boundary relations. Just to give you a sense of what it looks like, let me draw them here. So if we have a C-shaped tangle, that's a small C-shaped tangle near the boundary, say with state mu and nu, one can evaluate it to a factor, which is Kronecker delta of mu and minus nu times some power of minus a squared. And there's also a relation that allows us to collide. So if we have a part of a tangle that looks like this, we can collide it to the boundary. And this can be expressed as a linear combination of 2 state tangles. Sorry, can you say again? Yeah, it must end on the boundary marking. Yeah, that's what it is. Yeah, and also yeah, it should it shouldn't end on the vertices as well. So it should be interior of a. Okay. Yeah, so that's the definition of a stated Skein module. For surfaces, just like the usual Skein module acquires an extra structure that it's being a unital associative algebra, if a surface sigma has if the boundary of a surface consists of intervals. So for instance, when the surface is a polygon, say a triangle or a disk with 3 punctures on the boundary, then then we can put a boundary marking to be like 1 point in each interval, so that once we cross the interval, it would look like a prism where the boundary marking would look like these bunch of disjoint intervals that look like this. Then again, we can stack this along this interval direction, so we get a Skein algebra, which yeah, sometimes we'll just omit this gamma from notation for simplicity. Yeah. So now, oh, the sigma is a surface whose boundary consists of intervals. Oh, yeah, yeah, yeah. Yeah, I mean, if we just imagine a prism. Yeah, those are boundaries, but right now we're not putting any boundary markings there, so our tangles cannot end inside these. So our tangles can only end on these markings. Yeah, yeah, and so we can stack like one on top of another. Well, I mean, yeah, one can say these are or I mean, but it doesn't matter. Yeah, yeah, yeah. So those are called stated Skein algebras. Um, so to this end, yeah. Oh, yeah, yeah. It's very general. Yeah, that's right. Yeah. So actually, yeah, 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 yeah. Yeah, yeah, that's a very good point. So I'll, if I, yeah, hopefully I have enough time to introduce you like a notion of like what's a good boundary marking, basically. Yeah, yeah. But thanks for the question. But before that, like to finish up our discussion of locality, an important observation is that um, this status game module of this boundary marked three manifold is not just a vector space, but it has a bunch of module structure. So it's actually a bimodule. It's a left module over tensor product of stated Skein algebras of polygons, which are, okay, so dn is n-gon. So d of degree of v, one for each sinc vertices, sinc vertex of gamma, and it's the right module, the same thing over source vertices. And yeah, and it's very important to think of the Skein module as a bimodule rather than just a vector space. So yeah, this statement, it's pretty easy to see. So if we have some boundary marking, let's say it has a vertex, say of degree 3, then since we don't allow, let's say, tangles to end exactly on the vertex, we can just erase a small neighborhood of it. And then this is topologically the same as, you know, we can kind of pull a triangular prism out of it. So we kind of have like one end of a triangular prism. So whenever we have an element of a stated Skein algebra of a triangle, we can always stack it on top of this. That produces an action of Skein algebra. So combining all these, it endows this Skein module, a bimodule structure. Um, Now I can get back to your question. Um, Imagine the following situation where we have a three-manifold Y. It could have some boundary, but let's say we chop it up into, say, two pieces, Y1, Y2, with the surface, let's call the surface sigma. Um, and in this newly created surface, we can put some boundary marking, say something like this, and yeah, that there can also be boundary markings that just exist on the boundary of Y. Of course, this boundary marking cannot be random because, for instance, if we choose empty boundary marking, then that cannot fully encode the splitting process. So we have this condition called um, assume that this boundary marking of sigma, the boundary marking is induced how to say, induced from a spectral network. Or in our paper, we call this sigma is combinatorially foliated because foliated because it's the same condition as saying that this boundary marking, this graph um, is um, is the same as the space of leaves in the corresponding one-dimensional foliation of surface. But under this slightly technical condition, we have a splitting map, which is a homomorphism from, oh, property of sigma. Assume that, yeah. So yeah, just a, uh, yeah, okay, yeah. So actually, just to simply put, it means the surface sigma is constructed out of gluing a bunch of these quadrilaterals where two of the opposite vertices are punctured, and it is equipped with this boundary marking going from one vertex to another, and we're only allowed to glue these together along the edges in such a way that this vertex right now, which is a sink, it remains a sink. This vertex, which is a source, remains a source. And any such surfaces, we call them combinatorially foliated, in a sense that it has this one-dimensional foliation, which is the one-to-one correspondence with these points. Um, sorry, say again? Uh, yeah, yeah. Um, it's probably true, but I'll have to think about it. Yeah, but yeah, it's just this condition that the surface is constructed out of these elementary pieces. But once we have this, there's a splitting map. We can split the Skein module into two pieces. Y1, here gamma 1 is the part of the boundary marking that's on the boundary of Y1. Tensor, the Skein module of Y2 of gamma 2. But here, I should emphasize that this is, okay, let me just put a bar over it, just to emphasize that this is not a tensor product as vector spaces, but rather tensor product as modules. Meaning, in this boundary marking, it can have some internal vertices. And remember that for each such vertex, we have this module structure. And so the action of the status Skein algebra of that corresponding polygon on the left and the right should be identified. And once we have this, then we have this bimodule homomorphism. Yeah, so using this splitting homomorphism, we can split our three manifold into simpler pieces. And oh, well, it's what we prove in this. Yeah, so actually, before our paper, I don't think, like, I'm not aware of any literature where people consider boundary markings that's a graph rather than just disjoint unit of intervals. And what we observed is that it's really important to, like, once you consider graphs, it's really important to think of them in terms of these bimodules, because it's very crucial in constructing the splitting homomorphism. So when the boundary marking is just disjoint unit of intervals, then this is really just tensor product as vector spaces. So I mean that's what happens in case of surfaces. When we chop a surface into, say, ideal triangles, then the corresponding splitting homomorphism is really just an algebra homomorphism from the original surface to the tensor product in the usual vector space sense, tensor product of Skein algebras of triangles. Oh, yeah, so here gamma is inside, is on the boundary of Y. So we haven't added in this. Yeah, so yeah, on this side we don't have this in this part, because I mean Y doesn't know about sigma at all. Sigma is just some choice of surface that we just decided to cut Y along. So yeah, and gamma 1 is the part on the boundary of Y1, and gamma 2 is the part on the boundary of Y2 after we added in this boundary marking. Okay. Okay. I don't think I'll have enough time to talk about everything I prepared, but so I'll have to make some choices. And yeah, even though this won't be totally relevant to this construction, I think it's worth making a remark on this interesting fact that, so in case of surfaces, that is when the three manifold is a surface times interval, we can take a bigone, that is a disk with two punctures on the boundary. In this case, we can split a bigone into two bigones. And what do we get? We get the Skein algebra of a bigone. We got a map from Skein algebra bigone to tensor product of two copies of Skein algebras of bigone, which endows this Skein algebra a coalgebra structure. And in fact, this Skein algebra bigone turns out to be actually the Hopf algebra. And in this work of Cosentino, Ley, 2019, where they studied stated Skein algebra surfaces, well, one of the theorems that they prove is that the stated Skein algebra of a bygone is, as a Hopf algebra, isomorphic to the quantized coordinate ring of SL2, which is Hopf dual to UQSL2. So this is just like one nice topological way of thinking about quantum groups. So in the remaining 4 or 5 minutes or so, let me just point out some remaining main ingredients in our construction. Okay, so we have a way to split our 3-manifold into elementary pieces, and the second main idea is to take a particular quotient called reduced Skein algebra, or reduced Skein module. And one can think of this process of taking this particular quotient is really the process that what Abelianizes the Skein module. So the reduced Skein module, which I'll denote by SK with bar, is a quotient of the ordinary Skein module of this boundary mark 3 manifold by killing all the bad arcs. Which are nothing but arcs of the form. So arcs of the following form. So these are tangles that are kind of localized near a vertex of the boundary marking, where if it's a sink, and if the sign goes from minus to plus going clockwise, or if it's a source, and the sign goes plus to minus going clockwise, and these are the bad arcs. And we want to kill these elements. Actually, there's an intuition behind this. If you follow the spectral network construction, then one can actually see that these are exactly the elements or the monodromies that needs to be 0. So just to convey the intuition, in spectral network, we have a stratified abelianization, and through codimension 1 strata, we have unipotent transformation. And the unipotent matrix would have, in case of rank 2 case, it has this entry 0, and these are exactly the elements that needs to be killed for this abelianization. Yeah, and just to finish up, for the main theorem is that we have this map from Skein algebra of Y. We equipped with an ideal triangulation. And in fact, instead of chopping it up into ideal tetrahedra, it turns out that it's actually easier to chop it up into pieces, what we call the phase suspension. So for each face of an ideal triangulation, there would be 2 ideal tetrahedra that is adjacent to it. We choose a barycenter of these 2 tetrahedra. We connect them with this base, basically taking some sort of a suspension. this is what we call phase suspension. It is easy to see that once you're given an ideal triangulation, we can chop a three-manifold into these phase suspensions, one for each face. So we get a splitting map, mapping it into a bunch of these phase suspensions. Okay. Let me denote my SF for suspension of a face F. And we also pass to the reduced Skein module. Oh, Skein. And it turns out that this guy is almost abelian, and in fact, it embeds into quantum torus, which it's some quantum torus. It embeds into quantum torus, and turns out that the kind of relations that has to be imposed. So remember that in the splitting map, this is not a tensor product of vector spaces, but rather a tensor product of modules, so that we have to identify the action, algebra action on the left and the right. So those kind of relations, it turns out that those can be translated exactly to the quantized relations satisfied by the quantized shape parameters in quantum gluing module. So yeah, this is the map we constructed. And with that, let me finish. Thank you. Yeah. Ah, okay. Okay. So when you say harm, so do you want to? I think. For, well, I mean, I don't think that's true in general. I mean, for that, you need to consider. Yeah. I mean, for that, you need to think of scan categories instead, not the ordinary scan algebras. Okay. 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 Right. Sorry, by restriction to what? Okay. Okay. Yeah. 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 That means that's right. So yeah, there's a as I pointed out earlier, there's a different approach to abelianization that actually makes use of 3D spectral network. For that, we would actually have to put the 3D spectral network inside each ideal tetrahedron, and then yeah. Yes. As I was briefly pointing out earlier, really um, the part where abelianization happens is when we pass to the reduced Skein module when we kill all these uh, bad arcs. And yeah, if we use the 3D spectral network, then one can actually see that. So yeah, these signs plus and minus should they correspond to certain choice of lifts, either sheet number 2 or sheet number 1, and one can actually see that there's no possible lift um, if we use start from either this arc or this arc. Oh well, yeah. So this, um, yeah, yeah. So yeah, that's yeah. Yeah. So what we did is a generalization of this much older work of Vanahan and Wang from 2010, which was reformulated in terms of these stated Skein modules by Constantin and Ley. So they worked out a version for surfaces, and we generalized this to three manifolds, basically using some intuition or input from 3D spectral network. Yeah, and yeah, it's a work in progress to show that this map is equivalent um, to a construction coming from spectral network. And yeah, of course, even though um, okay, well, I mean, one might say if they're the same, then what's the point of using these two different approaches? And then like this map, there's a um, the expectation is that there's a pretty clear generalization to SLN, whereas in case of spectral networks, like counting all those webs is just, it's in general very hard.